Welcome. We are glad you're here. My name's Alan Love. I'm the director of the Minnesota Center for Philosophy of Science, and we are very excited about our event this afternoon. Our format today will include the lecture itself, followed by a commentary, and then after our lecturer responds, an opportunity for questions, general discussion, and then a reception out in the area that you walked through on the way in. Let me begin with a few words about the establishment of the lecture itself, and then I'll introduce our primary speaker, saving an introduction of the commentator until after the lecture. The Ronald Giere Memorial Lecture in Philosophy of Science is made possible by an estate gift from former Minnesota Center for Philosophy of Science Director Ronald Giere, who passed away in 2020. Giere taught in the Department of History and Philosophy of Science at Indiana University Bloomington before moving to the University of Minnesota in 1987 as Professor of Philosophy and Director of the Minnesota Center for Philosophy of Science. He was widely known for his work on models and scientific representation, articulated in books such as Scientific Perspectivism, which emphasized how models are like maps that represent the world based on conventions and purposes of the scientists who create them. As a result, they always offer particular and limited points of view. Giere was a fellow of the American Association for the Advancement of Science, a longtime member of the editorial board of the journal Philosophy of Science, and past president of the Philosophy of Science Association. We are grateful for his generosity to establish this lecture and committed to ensuring it serves as an enduring testimony to his scholarly legacy. Now it is my great pleasure to introduce Professor Roman Frigg to deliver the third biennial Giere Memorial Lecture in Philosophy of Science. Professor Frigg is Professor of Philosophy and Head of Department at the London School of Economics, Department of Philosophy, Logic, and Scientific Method. And he was Director of the Center for Philosophy of Natural and Social Science at the LSE from 2011 to 2020. He holds a PhD in philosophy from the University of London and master's degrees both in theoretical physics and philosophy from the University of Basel in Switzerland. Professor Frigg is also a permanent visiting professor in the Munich Center for Mathematical Philosophy at the LMU in Munich, and has held visiting appointments in the Rotman Institute of Philosophy of the University of Western Ontario, the Descartes Center for the History and Philosophy of Sciences and the Humanities at the University of Utrecht, the Sydney Center for the Foundations of Science of the University of Sydney, and the Department of Logic, History, and Philosophy of Science of the University of Barcelona. His research interests lie in general philosophy of science and philosophy of physics, and he has published papers on a diverse range of topics: climate change, quantum mechanics, statistical mechanics, randomness, chaos, complexity, probability, scientific realism, computer simulations, modeling, scientific representation, reductionism, confirmation, and the relation between art and science. His current work focuses on predictability and climate change, the foundations of statistical mechanics, and the nature of scientific models and theories. This past semester, the Center Discussion Group of the Minnesota Center for Philosophy of Science read his magisterial 2023 book, Models and Theories, A Philosophical Inquiry, and we were able to fruitfully discuss that with him earlier today. Professor Frigg has been quite busy in publishing over the past decade. In addition to numerous journal articles and book chapters, he co-authored Modeling Nature, an opinionated introduction to scientific representation, and Scientific Representation, both with James Wynne, as well as Foundations of Statistical Mechanics with Charlotte Ferndale, and The Fundamentals of Thermodynamics with David Levis. Beyond his extensive scholarship, Professor Frigg has served and continues to serve on a number of editorial and advisory boards. He was associate editor of the British Journal for the Philosophy of Science from 2011 to 2017, and a member of the steering committee of the European Philosophy of Science Association from 2013 to 2017. Additional service roles to the profession include the Advisory Council of the Institute of Philosophy at the University of London since 2022 and chair of the Management Committee of the Lakatos Award since 2018. Professor Frigg also has been awarded the Friedrich Wilhelm Bessel Research Award of the Alexander von Humboldt Foundation. Please join me in welcoming Professor Roman Frigg to deliver the third biennial Giere Memorial Lecture in Philosophy of Science.
Thank you very much for this very kind introduction. And thank you all for coming to this lecture hall on a sunny afternoon. So I would like to start by thanking the Minnesota Center for Philosophy of Science, in particular its Director Alan Love for inviting me to give this lecture. It's a real pleasure and indeed a honor to give the Giere Memorial Lecture here today, and I look forward to the discussion with you all after the lecture. So, I first met Ron Giere exactly 20 years ago at a conference in London. Shortly after that conference, I went on a sabbatical in Barcelona, and still having Ron's wonderful lecture in mind, I thought I should organize a conference in Barcelona and invite Ron as a keynote speaker. And so I did. The conference was entitled Models in Science, Semantics and Ontology, and I was lucky that he accepted and came, and we had a really good time. So we had impassioned debates during the day, and when the debates were over, we went for a drink together. And so I went through my family album, and so this is a photo of Ron and me at that Barcelona conference in 2007, having a drink together. I remember distinctly the first evening, so we were just having a good time, and at some point it was time to wrap up because the second day was waiting, and we all thought about walking home. But then Ron, being Ron, he had a trick up his sleeve. He said, no, I'm not walking home. He opened his bag and pulled out the folding bike, and he biked home. So that's Ron, as we remember and love him, and this lecture is obviously dedicated to him. In this conference, we discussed, as I mentioned, models broadly construed. And among the debates we had is what is an accurate representation and what does it mean for a model to fail to be accurate. Now that topic stayed with me, and this lecture builds in a sense on the discussion I had with Ron at the time, but I want to give the question sort of a practical twist. So rather say, what does it mean for a model to misrepresent? I want to ask now, what do we do with models that we know misrepresent? And so the problem is this: how can inaccurate models be a guide to practical decisions that we have to take? And this is where my colleague Richard Bradley comes into play. So once I realized that I was effectively wrestling with a decision problem, I thought, well, I have a colleague who knows about this, and I knocked at the door of Richard Bradley, who is a decision theorist, properly speaking, and told him about this, and that conversation led to a collaboration that has been going on for many years now. And I mentioned this because what I'm going to present in this lecture is material that Richard and I have developed in collaboration. So I want to give you a very quick preview of the lecture before jumping in, so that you have a bit of an idea of what the line of argument is and where I'm going with this. In section 1, I introduce the basic problem I am wrestling with. And this is that cyclones are here, they happen, and they are tropical storms that can have devastating effects. Now, these effects could be mitigated by taking protective action in areas that are expected to be affected by the cyclone before the cyclone makes landfall. And this kind of action is known as anticipatory action. Now, taking anticipatory action relies, as you would easily guess, on having forecasts, because one must know where the cyclone is expected to hit. If you don't know, you can't take any action. These forecasts are typically produced with scientific models. You see how we get to the Giere topic. But these models face scientific uncertainty, which makes the forecasts themselves uncertain. So we need a mechanism to manage the uncertainty and to make responsible decisions, given that we're basing these decisions on uncertain models. Now, how this is done in principle is the subject of the second section of the presentation, where I present the so-called confidence approach to decision making, which is a decision theory for decisions taken under uncertainty. In section 3, I will introduce a project that's called the Hazard Impact Tracker, or HIT for short. This project puts the theoretical framework that I introduced in the previous section into practical application in the context of cyclones, where predictions are made with a suite of modern weather model. I mean, the core aim of HIT is to produce an automated early warning system, giving decision makers warnings when danger looms, and it aims to do so in a way that is sensitive not only to the uncertainty in the forecast, but also to what's at stake in such decisions and the risk attitude that decision makers have. Finally, in the last section of the talk, I will briefly look at the case study, namely Cyclone Kenneth, which has hit Mozambique in 2019. We compare the alerts that would have been triggered by the HIT system with the alerts that have actually been triggered and what has actually happened. And what we find is that the HIT algorithm would have triggered alerts earlier and more decisively, and decision makers who were minded to follow these alerts could have taken actions earlier than they actually did, and that would have saved both lives and livelihoods. So the meta-philosophical subtext is that philosophy saves lives, literally, and I hope to have convinced you of that by the end of this lecture. Okay, cyclones and anticipatory action. So cyclones, hurricanes, and typhoons, they're the same thing. There's just different names for the same physical phenomenon when they occur in different parts of the world. They're effectively large air masses that rotate around the center of low atmospheric pressure. Now, as I already mentioned in my preview, we use as an example Cyclone Kenneth that hit Cabo Delgado province in Mozambique on the 25th of April 2019. Now, the effects were devastating. There were 45 fatalities, 373,000 people were affected in one way or another. 45,000 houses were destroyed, over 100 health facilities were damaged, and public health risks escalated in the aftermath, notably due to cholera. Now, that cyclone didn't come entirely unexpected, as we see later, but sort of the guiding paradigm that's still sort of the current paradigm at the moment in the face of such catastrophes is basically wait and fix. So humanitarian organizations got involved relatively late. So in the case of Kenneth, just one day before the cyclone made landfall. And insurance companies only get involved after the event. They basically wait for this disaster to play out, and then they send the loss adjusters and pay for the damage. Now, that's not a very satisfactory way of addressing such catastrophes. So we would be better off if we adopted a proactive paradigm, namely one that is based on taking anticipatory action. So anticipatory actions are measures that can be taken before the event. For instance, you can enforce a water line by putting sandbags out. You can reinforce home by installing storm shutters and secure roofs. You can reinforce health facilities, water points, and shelters. You can check the backup power systems. You can activate rescue response teams. And you can evacuate vulnerable segments of the population. And that's where the insurances come in. You could, for instance, pay for this by quickly paying out pre-allocated funds to cover the costs of these measures. Now, anticipatory action is increasingly advocated by humanitarian organizations. For instance, the International Federation of the Red Cross and the Red Crescent Societies, the START Network, the African Risk Capacity Network, and the United Nations Office for the Coordination of Humanitarian affairs, they all are now very outspoken that anticipatory action is the way to go, and this is the future of humanitarian interventions. Now, as I mentioned, anticipatory action relies on forecasts. If we don't have forecasts informing us where something bad is going to happen, then we cannot take anticipatory action. Hence, hazard forecasting is absolutely crucial to that endeavor. Without hazard forecasting, there's no anticipatory action. How do we get such forecasts? Well, the dream answer is, well, you take the perfect weather model, you generate the perfect forecast, and you act on this perfect information. That's a perfectly good answer if you have these perfect models. But from my rhetoric here, you will already have guessed that this is not quite how things go, because it's really a dream answer, and that gets us into the dreamy territory of a mythical creature of philosophers, namely Laplace's demon. So Laplace's demon has the following defining features. It has unlimited computational power. It has unlimited dynamical knowledge, which is sort of symbolized by the creature being sort of slightly brainy in its head. And it has unlimited observational power, allowing it to fix initial conditions of system with absolute accuracy, so symbolized by these laser eyes here. Now, doesn't take much convincing, I hope, to run the point home that none of this is available in the real world. So there is no Laplace's demon, and we don't have a telephone line to anything like Laplace's demon. So in the real world, there is no perfect model that's available to us. There's no perfect forecast, and so the dream answer is not available. On the contrary, what we're up against is model uncertainty. And the manifestation of this is that there are many imperfect models. So a symptom of scientific uncertainty about models is that models proliferate. So you have many models rather than one model, and it is impossible to decide between these models on the basis of available scientific evidence. As a result, scientists work with what is now called Model-Ensembles, sets of models, and that's really what forecasts are made with. Here are some relevant examples of this here. The European Centre for Medium-Range Weather Forecasting uses an ensemble of 51 models to generate its 6-hourly forecast. And these are the best forecasts you can have if you fly to the UK and you land in Heathrow, or indeed you land in any other European airport. These are the forecasts that are being used. Or the UK Met Office has an ensemble with 17 models. Or a couple of years ago, the Florida Commission on Hurricane Loss Prevention made an assessment exercise, and they used an ensemble of 972 models. I mean, they had a bunch of basic modules that they recombined in various ways, but it was really an extraordinary exercise sort of to use over 900 models. Now, one can, of course, speculate about the progress of science, but I'm pretty sure that in the lifetime of anybody in this room, this situation is not going to change, and we're not getting anywhere near a Laplace's demon scenario. So we better figure out what to do with model ensembles. So we have to make decisions under uncertainty with model ensembles. And this is just an observation about how the scientific community has reacted to these problems. There have been huge efforts to make models better, and these models really have got better. So these model suites that we have now are much better than the model suites we have 20 years ago. But efforts to develop forecasting tools have not really been matched by similar efforts to develop instruments for effective decision making based on these models. And hence forecasts often don't translate into action, which is also something we see in the case study that I have mentioned before. So the fundamental challenge is to develop instruments for effective decision making under uncertainty. And that's exactly what HIT aims to do. As I mentioned already, HIT is an acronym for Hazard Impact Tracker. It's a decision-making tool based on the confidence approach to decision-making, which I will introduce in the next section of this lecture, and that takes as a scientific input the European Centre 51 model ensemble of weather models. The implementation is online, so there's a computer platform for this that gives outputs in the form of alerts. It's fully automated. It's open access, so anybody who wants to use it can use it. It will be launched this summer, so it should go online. And we have a pilot project planned with Madagascar, where all this will be running from November onwards, which is the cyclone season in Madagascar. And then we see whether, if you run it in real time, it will be as good as in the case study that obviously works with a historical case. I will report on that on a future occasion. Now you can imagine that this is not something one can do by one's own. So this is a whole team behind that. I already mentioned my colleague Richard Bradley, who is my colleague at the LSE. But this is done in a big project that was funded by UKRI. This is the Innovate UK Research Council. It's coordinated by Maximum Information, which is a climate science and weather science consultancy startup. The meteorology unit at the University of Reading, and it involved the British Red Cross for the humanitarian sector and Aon Insurance for the insurance sector. So all these actors have been involved in this, and you will hear throughout the lecture what role they played. So let me then turn to a bit of good philosophical theory here and introduce the confidence approach to decision-making under uncertainty. So the confidence approach offers a decision mechanism based on the scientific evidence available, the confidence an agent should have, what's at stake in the decision, and the uncertainty attitude that an agent should have. Now the core insight, which hopefully is more or less commonsensical, is that the level of confidence that we should require to act depends on what's at stake. So let me take you through this decision theory in a number of steps. So the first step is to pick a variable of interest to you in your decision problem. That can be a probability, for instance, but in our example, they are physical variables pertaining to cyclones, like maximum wind speed, precipitation, central pressure, and the like. And then you construct nested intervals in which the values of these variables could lie, which is symbolically represented here. The next step, and that's a crucial scientific step, is the confidence grading of these intervals. So you confidence grade these intervals by examining the weight of the scientific evidence supporting the claim that the actual value lies in a certain interval. And here we can be maximally pluralistic. So you just help yourself to absolutely anything that's available in the arena of science. If there are statistical methods that help you do it, that's great. Use statistical methods. But if not, you can use skill scoring of models, which is something that's often done in this context, or you can have an expert elicitation exercise. You ask the physicists who construct and run these models how good certain models are, how much trust one should have into certain values. You really absolutely anything you can get your hands off by way of scientific evidence should be considered here. And then you attach a ranking to the intervals that you have constructed. And at this point, for the purpose of HIT, we make a conventional choice. we just say that 3 levels of confidence: low, medium, and high. One could fine-grain this in any way you like. You can have 5 or 7 or an infinity that is quantified by real numbers. So nothing hangs on this. This is a choice just to make things simpler. And then logic dictates that we have less confidence in more precise claims. So you get a picture like this, where you have high confidence in the broad interval, you have medium confidence in the medium interval, and low confidence in the narrow interval in the middle. So that's the scientific part of the project. Now we change over to the agent side and ask, what's going on at the side of the decision makers? And first we ask, well, what's the stake of the decision? And this is effectively an assessment of how important a decision is to an agent. Hopefully that's intuitive. Some decisions are important, some decisions are not so important. So if I am a bet a beer with my friend about who's going to win the next soccer game, the stakes are not very high. But if someone puts a pistol on my chest and asks me a difficult question and I know I get shot if I get it wrong, then a lot depends on it. So that's what we're trying to assess here. And we choose a conventional scale here. So basically 0 is when not much at stake. That's the beer scenario. And 1 is when a lot is at stake. That's the pistol scenario. And so the first thing a decision maker has to ask himself is, what's at stake for me in making a decision? Once this is clear, the decision maker has to ask himself how much confidence is required to make a decision at a certain stake. And the answer to this is a so-called cautiousness function. And this cautiousness function represents the uncertainty attitude that an agent has. And that can be different for different agents. So here's an example of such a function. So an agent could say, for a decision problem where the stakes are between 0 and 0.25, I'm happy with low confidence. But between 0.25 and 0.5, I need medium confidence, and everything above 0.5, I need high confidence. But another decision maker could say, no, that's too much caution for me. I'm happy to make decisions at low confidence between 0 and 0.5. I need medium confidence between 0.5 and 0.8 and high confidence above that. And you see that these decision makers don't require the same level of confidence for the same decision. So say if a decision has the stake of 0.4, the cautionary attitude on the left would require that we have medium confidence, while the more risk-taking attitude on the right would say that low confidence is enough. And I don't think there is right and wrong. So you just have to ask decision makers, what kind of decision maker are you? What do you require? Now with this you can select your interval. If you, say, to stick with the example before, have a decision that has a stake of 0.4. If that is your cautiousness function, then you require medium confidence. Then you look at your scientific confidence grading of relevant values. You figure out that the middle interval, the purple interval, is for you, and that's the interval on which you base your decision. The last step is that you apply a decision rule to that interval. And so here is a rich literature available in decision theory. There's a few obvious candidates are maximum expected utility or robust decision making, but I won't go into these because I don't use any of these in this lecture. So in the case that we're discussing here, the decision rule is a trigger on a color-coded alert scheme, and I will say more about what exactly that is later. So that's the summary of the procedure. You start with the decision problem at the top, and then you can go down the science branch, where you first construct nested intervals, and you confidence grade them by taking the evidence into account. Then you look at the agent branch, where you ask, what's at stake? How much caution do we require? They come together in a selection of the relevant set of values. Then you apply a decision rule to that set, and then you make a decision. So that's That's the scheme in the abstract. And that brings me to the next section of the talk, namely the HIP Hazard Impact Tracker, which, as I mentioned, is the project of applying that abstract decision theory to the concrete case of cyclones. And what I want to do is sort of go through all these steps and say how they're filled out in that concrete case, and then illustrate them with the case study of Cyclone Kenneth in Cabo Delgado. I should put my hands up at this point and say more work has gone into the science branch than into the agent branch so far, and if you have any interesting idea about how we could flesh out, say, the stakes of decision makers in that context, that would be very much appreciated. So let's start with the decision problem. Now here we have a decision maker. Let's call him Bill. And the Bill asks to act or not to act. That's the question. So that's the problem we have. And obviously the action we're talking about here is anticipatory action in the face of an impending natural disaster like a cyclone. But now, rather than going through all this sort of basically from top to bottom, I want to fast forward to the decision rule, which I very quickly skipped over before. I just said this is sort of a color-coded alert scheme, and say something about that, and then come back to the other point. I promise you I get through all of these in my presentation. So, what we want to construct effectively is a trigger system. So we need a trigger that triggers a warning when something happens or is expected to happen. And as I mentioned at the beginning, to do that, we look at relevant physical variables that characterize cyclones, like the maximum wind speed, typically sustained for 2 minutes, the central pressure or precipitation, or many others. I mean, those familiar with the physics of storms will know that this is a long list of relevant variables. Now, what we do, or what we have done so far in this project, is just focus on maximum wind speed. This is because it is a crucial characteristic of hurricanes and cyclones and is easy to understand by stakeholders. And more importantly, it is something that we could squeeze out of the forecasts with the computational resources that we had, because it's actually a lot of work to get it out of the ensemble forecasts. But we are working on further versions where we also want to take a precipitation and then central pressure into account. But that's for the future. In this lecture, I work just with maximum wind speed. But the focus for a trigger has to be decision making for a particular area A. So you want to know what happens in a particular area, and because we want to know this with an eye on anticipatory action, it's sensible to choose the area so that this is an area that has an infrastructure that can be mobilized to implement actions. And so that's most naturally the case in an administrative area of a country. I mean, from as far as the scheme is concerned, you can take any area. You can take your back garden, if you like. But that's not a good way if you want to plan anticipatory action. So what we did is just take the administrative areas of Mozambique as the relevant areas, and we ask, what are the triggers for anticipatory action in these areas? Now, as I said, the aim is to produce trigger warnings in advance so that decision makers can act. And here we revert to a well-established system, namely the so-called GDAX system. And GDAX is an acronym that stands for Global Disaster Alert and Coordination System. And this has sort of a traffic light system with green, medium, so green for low impact, amber for medium impact, and red for high impact. And so you can trigger one of these 3 alerts in that system. Now, which alert you trigger in that system depends on the wind speed, the population, and the vulnerability. And this is sort of how it's defined. I'm not talking you through every line individually. What matters is just that you get the gist of it. So, for instance, you get a green alert if the maximum wind speed is between 17.5 and 33 meters per second, if the population is smaller than 10 million and the vulnerability is basically anything. You get an orange alert if it's in the same range of wind speed, but the population is greater than 10 million and the vulnerability is high, etc., etc. So that's how this is defined. So that's not something we have come up with. That is a widely used alert system in the humanitarian sector. And you see why this is useful. So the wind speed is obviously exactly what speaks to the science branch of the confidence approach, and the population and vulnerability, they feed into the agent branch, most notably into the assessment of the stakes. So if the population is large and is vulnerable, the stakes will be high. If the population is small and not vulnerable, the stakes will be low. So you see that these considerations map rather nicely onto what the confidence approach wants as an input anyway. But now you wonder, okay, the GDAX system gives you this sort of traffic light system with wind speeds, but what we get out of the confidence approach is these intervals. Now, how do they relate to each other? Here's our little decision maker friend who is sort of somehow puzzled about this. So how do we bridge the gap between what the warning system wants and what the approach gives us? The answer is surprisingly simple. Just think about what these intervals really mean. So what these intervals tell you at a certain confidence level, L, and L is medium, low or high, the maximum wind speed will not be outside the interval. So, I mean, that's how the intervals have been constructed. That's what the intervals mean. That also means that the wind speed will not exceed the upper bound of that interval. And so you realize immediately that the upper bound of the interval is effectively what has to go into that qualified range in the GDAX classification system. So we've solved that problem. So now let's ask where all this comes from. I've now just told you, well, if we have these intervals, that's how we use them. But where do the intervals come from? So how does that work? They're not suddenly dropping from the sky. And that's a lot of work. How do we get to these intervals? Recall, and that brings us back to the observation that we don't know Laplace's demon and can't get our hand on perfect forecasts. There is no perfect model. We have to work with Model-Ensembles, and the ECMWF ensemble has 51 ensemble members, so we have to work with these somehow, and we have to turn that into intervals. We get an idea about how to do that if we ask ourselves sort of very abstractly, what kind of outputs do these models actually give us? And what they do give us is a storm track. So it tells you the trajectory of the center of the storm for a time t in an interval from 0 to capital T. And the capital T is then the lead time. De facto, this is up to 10 days into the future. So what every model in that ensemble gives you is a storm track of where the center of the storm goes for the next 10 days. And that comes with a specification of the maximum wind speed at every point. As I said, the ECMWF produces an ensemble with 51 forecasts, and it does 4 forecasts every day. So you get one at midnight, one at 6 in the morning, one at noon, and one at 6 in the afternoon, and up for 10 days into the future. And in practice, this looks something like this. So these are the actual forecasts at the time. So we went back to the archives and dug up the forecast, and that's the forecast on the 17th of April at noon. You see that something's going to happen out there in the Indian Ocean, and you see the various tracks of the Model-Ensembles. And that's how it looks like on the 19th of April. starts getting more focused, so all the spaghetti start lining up. On the 21st, it starts dispersing a bit again. But finally, on the 23rd, you see that something sort of bad is going to happen in northern Mozambique. But now you have the next puzzlement. So what you get out of the models are these sort of spaghetti figures over a map. But what the confidence approach wants is need intervals. Well, how do we get from one to the other? So recall, each model outputs a predicted storm track, which is the center of the storm at the maximum wind speed. Now that, trivially, gives you a set of maximum wind speeds in the area A at a given time t, and we have that for every 6-hour interval up to 10 days into the future. And here I want to give a shout out to my colleagues who do the modeling. I'm giving you sort of the meta story quickly here for the sake of conceptual clarity. Doing all this is an awful lot of work. So really a big thanks to people who run these models. But if we have these numbers, the task is basically to convert 51 numbers into an interval and confidence graded. There's different ways of doing that, and we discussed them in a theoretical paper that is sort of foundational for the approach. The reference is here. I'm also happy to send it to you if you want to drop me an email. And it's a modeling fact that the forecasters insist that the 51 models are independent and equally likely. So it's not the case that one model is better than the other. So all models bear equal epistemic credence. And we argue in the paper under this scenario, and only under this scenario, there may be different scenarios where one model is best and you can center on that model, but under the scenario where those who know these models best, namely those who construct and run them, insist that there's no way to distinguish between them, you should use statistical nesting. And that just means that you calculate the means and the variance of the 51 numbers. And then we say that the low confidence interval is the means plus minus 1 sigma, the medium is the means plus minus 2 sigma, and the high is the means plus minus 3 sigma. So this is how the intervals are constructed here. But I want to emphasize again, this is just because the ensemble is such that all models are equally good. With a different ensemble, this could look completely differently as a construction. Good. So we've dealt with the science branch. Let's now talk a bit about stakes. And as I already said, that's a bit of a building site still. We're working on it. But these are the considerations that would go into assessing stakes. And here it gets interesting because the assessment of stakes is very different for humanitarians and for insurers. So if you're a humanitarian, there's effectively 2 dimensions to assessing stakes. One are facts on the ground. So that's how big is the population and how vulnerable is the population. And you see again the GDAX considerations cropping up here. And the second is facts about the organization. You want to worry about resource allocation. So mobilizing for an emergency may imply under-resourcing other cases. And trust and credibility may be undermined when too many false alarms have been issued. So it's the cry wolf problem. So humanitarians have to ask themselves, well, how many alerts can they actually afford, and how many alerts should they reasonably issue, given that there can be false alarms? And all this will then feed into an assessment of the stakes for the decision to call a certain alert. If you're in insurance, you need not pay attention to these considerations. You can just say, well, my stakes is my financial exposure. So how many contracts do you hold in that area? What's the structure of the portfolio? Are all your contracts in that area, or is it just 1% of your portfolio? What are your reinsurance arrangements? Are you going bust if you have to pay out for a disaster, or are you comfortably reinsured? And things like that. So for an insurance, the stakes depend on these sort of things. As you see, it's very different than it is for humanitarians. Now, what about caution? Again, this is different for humanitarians, for insurers. So humanitarians will ask themselves, so how much damage can one accept? Can you live with one person dying, but you can't live with 100 person dying? So how you assess the damage that you can accept? How much wasted resources in the case of a false alarm can you justify? So it's one of the interesting things in discussions with humanitarians is that they're extremely concerned about justifying their use of resources to their donors. So they're very concerned about false alarms, because if they call false alarms, they may not get funding next year. So that will go into their cautiousness, or how many trigger events can they afford every year? So can they trigger once? Can they trigger 5 times? So that's the sort of things that will go into their assessment of cautiousness. So insurers will just ask themselves how much risk can they afford, and what happens if the disaster actually strikes. Good. All this in place, you select the set, you know which set you have, and then you apply your decision rule to it, which is using the GDAX traffic light system, and that is effectively your decision making. So that's how it's implemented. So I have taken you through this already. And so then we feed all that into a big computer and run the calculations. And in the calculations, we just assumed that the vulnerability of the population is medium to high, which we assumed on the basis of humanitarian reports that we had available. And we don't make a decision on cautiousness, because we just produce forecasts for all levels of cautiousness. So we can see how a cautious, a medium cautious, or a not so cautious decision maker would act, which is interesting in its own right. But the basic structure of the output is here. You see at t equals 0, which is the next 24 hours, no alert is triggered, and that's on the 23rd of April. Remember, the cyclone made landfall on the 25th. So what the calculation gives you for high confidence, chosen stakes, chosen cautiousness, medium vulnerability, and actual population sizes, no alert for lead time T0, that's the next 24 hours, a red alert for T1, that's between 24 and 48 hours into the future, also a red alert for T2, that's between 48 and another 24 hours in advance, and so on and so on and so on. And you get a green alert, the green alert for until T5, and then no alerts for T6 to 9, and that pretty much realistically reflects what the storm did. That's a schematic representation. In practice, the outputs look like this. So you see Cabo Delgado, and here we have 9 levels rather than only 3, because we did stability checks. So always look in the middle. So at the left, sorry, this is very small here, you see 3 low, 3 medium, 3 high. When you look at the middle one of each of them, that's just the interval that comes out of the confidence approach. And then we wanted to control for boundary effects. We repeated the calculations by just taking 2 meter per second wind speed off and adding 2 meters per second to see whether our decision is just at the borderline. And in some cases it actually is. You see that here you have borderline effects here, but in that actually changes, so you know that the effect is borderline. But basically, you have the confidence levels, and you have in the vertical, you have the lead time in the horizontal, and you get, for every confidence level, you get an alert level. And now the decision maker can say, well, given my theoretical commitment, I need medium confidence, so I have an amber alert for t equals 1, and that's what you would hand down to the political decision makers. Whether they actually act on your alert is, of course, another question. There's a whole discussion about how alerts are actually processed. That's beyond the scope of this project. We just look at the alerts. And that's how the system functions. And that is how the HIT platform implements this confidence approach to decision making. And now, just very briefly, I won't keep you for much longer. I just want to say how this plays out in the case study that I have mentioned. And that is joint work not only with Richard Bradley, but also Ada Meltzer, who was a student at the LSE who helped doing some of the data processing and the analysis. So we take Cyclone Kenneth and we look at what actually happened, and we compare it to what would have happened had one used HIT, and we see a stark contrast here. So here is what actually happened. That's the historical record. So we just see the days here, sort of the 18th of April down to the 25th of April when the cyclone made landfall. So you had a green alert on the 22nd, you had amber alerts on the 23rd, and you had a red alert only on the day when the storm actually made landfall. Now, the counterfactual history of this is here. So that's what the HIT system would give you. So if you're a cautious decision maker who requires high confidence to act, you would have got a green alert as early as the 18th of April. So that's an entire week in advance. If you're a medium decision maker, you would have got your green alert on the 20th, which is still 5 days before landfall. And even if you have a low confidence decision maker, then you would have got it a day earlier than you actually got. I mean, arguably, given the area, the population size, and the vulnerability, you should be in the high segment. So you would have got alerts much earlier, and you could have acted much earlier if you had the HIT system rather than the actual alerts. And if those in charge of actually implemented action on the ground would have acted on these alerts, as I said at the beginning, lives and livelihoods would have been saved. And so here is philosophy's contribution to saving lives. And on this note, I say thank you so much for listening.
So it's my great pleasure to introduce Dr. Samuel Fletcher, Professor of Philosophy of Physics in the University of Oxford's Faculty of Philosophy and a Fellow of Merton College. Prior to this, as many of you know, from 2015 to 2024, he was a professor in the Department of Philosophy here at the University of Minnesota. Professor Fletcher is currently a resident fellow of the Minnesota Center for Philosophy of Science and an external member of the Munich Center for Mathematical Philosophy at LMU Munich. Professor Fletcher's research focuses on the foundations of physics and of statistics and how problems in these fields inform and are informed by broader issues in the philosophy of science. He also has interests in the conceptual and physical basis of computation, metaphilosophy, and the history of physics and philosophy of science. He's currently the PI of the NSF-sponsored Career Project, a modern philosophy for classical statistical testing and estimation, and recently published Foundations of General Relativity. Recent articles include on the alleged incommensurability of Newtonian and relativistic mass, inner Kentness, and the representation and determinable structure of quantum properties in Synthèse, co-authored with another faculty member in the Department of Philosophy here, David Taylor. Professor Fletcher also serves as co-editor-in-chief of the European Journal for Philosophy of Science. Sam, welcome back to Minnesota. The floor is yours.
Thanks very much, Ellen, and it's so good to see so many of you again. Instead of, as is often philosophers want, to start in on the criticism of Roman Frigg's presentation, instead I want to tell you how I see the work that he's doing is being situated among other kinds of work, and then ask certain questions that I think having a discussion about will help us understand more about how the proposal of the confidence approach to decision making in this specific application work. So first, I'm going to tell you a little bit about this context, and then mostly I'm going to be talking about the comparison of this sort of approach to much more simplistic approaches that maybe some of you might have heard of that raise the question about what's really great about Roman's approach. And that will be a question that I'm hoping that we'll be able to discuss in the question period. And in the very end, I'll talk a little bit about convention, or maybe put another way, the role of objectivity in the kind of decision-making processes that we're talking about here. So let's start in on context. Now, I think it was discussed very clearly that we're in a situation where we're taking advice, expert advice, from a scientific model. And if we had the perfect model, we'd be able to make the perfect predictions, and so we'd be able to make the perfect interventions, the perfect decisions. But because we don't have the perfect model, we have many different imperfect models. We have to decide which predictions we want to believe, or maybe something in between the predictions of them. And these models can be imperfect in many different ways. They could be imperfect because they don't agree on which data to use. It's because that they use distinct data, or they could use different equations, right? They could use different physical theories or models. I'm not going to tell you about the details about how all of these things can work, but to look at one example that we saw from the slides from before of this very nice spaghetti plot, you can see over here that a very nice red trajectory, and then at a certain point you get a spaghetti explosion. Do you see the explosion of spaghetti? Okay, good. And you'll notice here that the endpoints of the spaghetti are not all exactly in the same place. The way that some of these models work is they recognize that the meteorological data that is taken is imperfect. It doesn't measure everything with complete accuracy. And all these slightly different endpoints of the spaghetti correspond to different perturbations of the data. You take the numerical data that the meteorologists have and you just change it slightly so that it's entirely compatible with what the measuring instruments said. But it's just a little bit different. The reason why that's significant is, of course, that meteorological systems are chaotic. The way they evolve depends highly sensitively on the specific details of the conditions of the meteorological system. And so just by perturbing the location of the cyclone very slightly, you can get totally different differences in how the cyclone is going to play out in its future trajectory. Okay, so this is an example with models with slightly different data effectively, but there's other ways in which you can have many different models. So you can think of the situation here as a situation like the following. We've agreed to defer to an expert panel, but the members of the expert panel don't agree with one another about what advice to say. So now we're in the unfortunate situation where we have to decide, what do we do given that we have the advice of this expert panel, but all the members of the expert panel give us slightly, sometimes very different advice about what's going to happen? And so the decision procedure that we've been learning about is a decision procedure in this sort of situation where we have to deal with a disagreeing panel of experts. In this particular case, the experts are weather models. But the general phenomena that Roman Frigg is talking about is a phenomena that we encounter in lots of different situations, not just with weather, in making criminal decisions and making other sorts of policy decisions, when giving advice from our friends. I don't know about you, but I've not been so lucky that when I seek advice from friends that they give me the same advice. So then I have to decide what I'm going to do. And we're facing the same situation here. Let's now compare the proposal of the confidence approach with a much more simple means of making decisions. I'll call it the weighted average method. It's exactly how it sounds. Let's just assume we have two models, M1, M and M prime. If we trust them equally, the prediction that we should make is just the average of that prediction. If we trust, say, model M about twice as much as model M prime, then we should weight it accordingly. You can see over here, we've given a weight of 2/3 to M and just 1/3 to M prime. This has lots of nice properties. It minimizes certain rates of error if these predictions are numerical. And these coefficients represent the confidence or credence that you might have that each respective model will be right. And this comes about just because you've decided from the beginning that you're going to defer to this panel of experts. So you've decided to invest your credence in what they say. Now, this is a pretty simple, even I would say simplistic means of coming up with a prediction for quantities like maximum airspeed. And the way that it would feed into making a decision is equally simple. You make a table, like I've given here, of the net costs. Landfall, no landfall, intervene, don't intervene. It's a complicated procedure, and it follows the same sorts of procedures that Roman Frigg was describing about considering what different stakeholders take to be important and how important. I put in some more or less random numbers in here to give you a feel for the flavor of what this would look like. So for instance, if you intervene and there's no landfall, you have to accept the cost of having acted unnecessarily. If you do and there's landfall, there will be damage, but the damage will be less than if you hadn't intervened. And of course, if you don't intervene and there's no landfall, then there's no cost at all. On this simplistic way of doing things, you just weight each cost by the probability of landfall or no landfall. That's the expected value of each choice, intervening or not intervening. And based on these, you pick the decision that gives you the higher expected value. So this is a standard procedure in decision theory. It's a lot simpler than the one that Rowan was talking about. So it raises the question, what are the comparative advantages of this more complicated procedure? Particularly, we can configure the numbers to give really similar results in specific cases. And it doesn't require the complicated confidence grading, cautiousness functions, and so on. So it'd be really helpful, I think, to try to understand what does the more complicated framework give us that these simplistic methods don't. Here, I'm reminded of a common phrase by a statistics colleague of many of ours, Charlie Giere. It's common enough to be known, I think, as a Gierism. Today's Gierism is, it's a thing you can do. Charlie Giere says this when there's a proposal for a procedure that does a thing, but, according to Charlie's complaint, does it derive from some deeper underlying theory? Is it demonstrably better than known alternatives? The fact that it's a thing that you can do doesn't mean that it's a thing you should do. That's Charlie's insight here. And I think it's a question that's worth investigating in this new proposal. Lastly, I'll come to the question of convention, or as I mentioned at the beginning, in other words, the objectivity of these sorts of decision procedures. You might have noticed that we have to make a lot of decisions at various points about how we feel about things. So for instance, we have to decide, how do we construct the nested intervals? How many nested intervals do we pick? Where do the divisions between low confidence decisions and high confidence decisions go? How exactly do higher stakes require higher confidence? Which decision rule should we pick? The concern here is not that these are bad questions to ask. They are good questions to ask. But the concern is that if they're flexible enough in how we answer them, then that flexibility can ultimately lead us to make any kind of decision that we might have liked before. The worry, in other words, is this just a technical license that allows us to go with our gut? You can imagine a situation where some initial choice of cautiousness functions and stakes and coarse graining into high and medium low gives you an answer that you think, that doesn't sit well with me. So let's go back and revise. We must have gotten wrong our cautiousness function. We must have gotten wrong how to coarse grain different risk levels until things sit right again. But if that's ultimately the procedure that we'll use to be able to determine what these are, then why didn't we just go with our gut in the beginning? I think that Roman Frigg has a lot to say about these questions, and so I'm glad to invite him to do so.
So while Roman is briefly responding to Sam, I just want to highlight that we will move straight into Q&A. So if you have a question, please raise your hand, and we've got floating mics that will run around and make sure that Roman can hear your question.
Yeah, thank you so much, Sam, for these wonderful comments. I'll respond briefly only in the interest of also making room for your questions. So why not average? The concern is that averaging loses a lot of valuable information about extremes. Imagine a suite of models of water levels in the Mississippi River. I don't know where the levels exactly are, but say one says 1 meter, 2 meter, 3 meter. And then you average, and out comes 1.5, and you decide, well, that's all good. But one model actually had 3 or 4 meter, and that means flooding. And you're losing that information when you average. So it's very important that you keep track of what the spread of your results is and what is the potential set of things that can happen. And that's not merely philosophers being nitpicking. The whole thing got started by an insurance company calling us up saying, we've read a paper of yours where you talk about modeling and risk. Can we talk to you? And at first I thought it was a prank, but no, because that an insurance company should be interested in philosophers is a rather outlandish notion. But it was real, and we started talking to them. And what happened was that they did exactly that. They just took the models, they averaged them, used them for decision making, and they racked up colossal losses 3 years in a row. And then we looked at the data, and it turned out that there was a huge spread. And averaging is a neat cover for this that makes you blind towards what can potentially happen. And the confidence approach, by sort of using intervals rather than points, takes this into account. So that's one thing I would say about why sort of averaging is potentially problematic. Now about, this is something you can do, and this is just retrospective rationalization of what you want to do anyway. Well, if you're really cynical, you can, of course, do that. And I mean, you can always do that with everything. But a serious decision maker would, of course, set these parameters prior to actually making decisions. So when we run the pilot that starts in November with the decision makers in Madagascar, we already start in May having the first meetings where we talk to them about stakes, we talk to them about cautiousness. We have several workshops with them where we sort of elicit them, and then we actually want to hold them to it. And I think if you take your own thinking seriously, that's what you should do. But even if you're not willing to do that, there is another twist to this, and this is where insurance come into play. So I've said relatively little about insurance, but insurance is interesting in the context. because they want to write insurance contracts that not only cover damage, that also cover anticipatory action. How would that work? So that's a branch of what's known as parametric insurance. That's insurance that pays out not on an assessment of loss, but on certain predetermined variables reaching certain values. For instance, you can buy storm insurance in a parametric sense if they just set the maximum wind speed, and when that maximum wind speed is reached, insurance payout happens no matter what the damage is. And that can be done in an anticipatory way. They could say, if 5 days in advance an orange alert is issued, you have an insurance policy that pays you so and so much to take anticipatory action. Now, that can't be done on a whim, but saying someone looking at it saying, oh, that doesn't sit well with me. So what insurance wants is that this entire algorithm on which that decision is made is part of the contract. They would write all this into their insurance contract and say, if this algorithm or something similar to it gives you this alert with this particular lead time, then you get so and so much, and that would be written into contracts. And that's why it's actually really important to have an accountable and traceable a procedure that determines what the alert is, because that's when you can write an insurance contract on it. So that's one of the clear advantages of having that. And if the decision maker then says, I actually would have liked it differently, the insurance will say, well, that's too bad, you should have made up your mind before. So I want to leave it at that. Happy to discuss more with you at the reception, but I want to give the audience time now to ask questions.
Good. Okay, so let me come around and please keep your question as succinct as possible so we can get as many in.
Thanks. That was terrific. Really interesting. Thanks to both of you. I'm just curious to know, in the confidence approach on the agent side, do you have to aggregate individual decision makers and do you have to somehow aggregate their risk tolerance, and how would you do that?
Yeah, that's a good question. So the question is, who makes the decision? I mean, in the case of Madagascar, it will be a government agency. So eventually they have to make a decision, but they have to explain this to their electorate in a democratic process. So there is a very good question, and you're right to highlight that. So whose decision, whose stakes, whose cautiousness? But eventually someone has to call the shots here. Someone has to issue an alert. And that someone has to answer that question and ideally justify that to the people who are affected by the decision.
So thank you so much to both of you for all you've said this evening. My actually question is kind of similar to the previous question, kind of thinking about the democratic process of decision making, but more I'm interested in kind of the question of trust. And I can see in a lot of ways how like these more convoluted like confidence approach can degrade potentially trust in kind of decision making if it's done by this panel of experts. So I guess, how does one mitigate that in your view?
Yeah. Look, I think transparency is what really matters. Whoever makes the decisions will have to explain how they have come to the view to which they have come. And part of this is public. I mean, there are reports on vulnerability, for instance, of various areas. And vulnerability will play an important role in assessing the stakes of a decision. And ideally, I think a government agency would eventually come out and say, we're using that algorithm. We have assessed that the stakes are this and this and this. We want to make decisions with this and this cautiousness function, and that's how we operate. So, and then the population can come out and say, no, that's not right. And then ideally that would be discussed in a democratic process. But I think the key to building trust is transparency.
Yeah. So I want to return to your answer to Sam's question about why not just use the average expected wind speed, say. And I took the point of your answer, right? There's information lost that we can keep with the intervals, but it seems like somebody could run your objection on your 3 interval thing, right? Because it feels like what we want is the probability distribution of the various wind speeds. Because let's say we care about the high confidence, right? So we look at the narrowest interval. It still matters a whole lot whether in that interval the probabilities are distributed in sort of a nice normal curve where the peak is somewhere in the middle, or if it's some more chaotic thing where you've got maybe a peak at one end and a peak at the other, right? I would make very different decisions given those 2 distributions. And it seems like that information's lost in simplifying even to that kind of information is still lost, even when simplifying to the 3 interval rather than just the average or mean.
Yeah, look, you're always losing information somewhere. The question is, how much do you retain? And the interval schemes retains much more information than a scheme that just keeps the average. That could be further refined. I mean, I use these 3 intervals because it's simple but the approach could actually use intervals that are not singly connected, that are bimodal. All that is completely compatible with the approach. In the particular example that we're looking at, I don't think it would matter much, because you remember the slide when I asked, well, how do these forecasts map onto the intervals? We figured out that, well, all that matters is the upper bound of the interval. So you don't actually care much about the distribution inside. But you could, in principle, refine that. I mean, there is no prohibition against this, and you could have 7 levels of confidence rather than only 3. So I think we would be very open to looking at such cases if needed. So this was just the beginning, because it was more sort of the scientific frame of mind. So let's start somewhere and then let's improve. So that was the idea. I mean, something I would have liked to do and which we couldn't do just because of the computational cost is actually not using statistical nesting, but so take the outermost points, because in nonlinear models you often don't have nice Gaussian curves. So you could construct the intervals by moving from the outside towards the inside. So you say we have 51 points. You always take the smallest distance from the edge towards the inside. We do that 17 times. That gives us the middle interval, and to do it another 17 times, it gives us the narrow interval. They would have come out looking different. I think it's an open question, and one that we very much worry about is how much would it influence the final outcomes if we did that. So, I mean, what's the robustness of the procedure, which is also something that was present in Sam's comments. So I think all these concerns are very well taken. I mean, I don't suggest for a moment that this is the final word on the matter, but I hope it is a first step in the right direction.
Professor Frigg, this was really fascinating. I'm thinking also with Dr. Fletcher's intervention, I'd like to bring Gerd Gigerenser's work on adaptive heuristics, fast and frugal heuristics, because I think that last point about the provocation and question on the technical license to go with one's gut, it's something which Gigerenser would answer, or the line of adaptive heuristics would answer very differently. And I do see the confidence approach and the anticipatory action approach as paired with that, and in the realm of decision making under uncertainty, and not the insurance company's interest of modeling uncertainty as risk. So that's one. And very quickly then, a question on trust. So to use the analogy of a room of experts or committee of experts, what if there is a Byzantine expert, like an adversarial node, in that the model ensemble would never work for that kind of expert or decision maker. And this, of course, relates to the question about government intervention and how this the confidence levels are passed at the level of public functionaries too.
Sorry, just to understand, would the adversarial expert be a particular model in the ensemble who disagrees with all the other models? Is that what you have in mind?
Yes, yes, yeah. Approximately, yes.
Good. Yeah, let me start there. Again, I would defer to scientists at this point, but if that so-called adversarial model is a model that you cannot rule out given what you know about the physics of the system and the data you have, then you should keep it in the model. So model ensembles shouldn't be sort of forceful whipping and groupthink. I mean, that's why you have model ensembles. And if you have models in the ensemble that do fundamentally different things, then that's a good thing. And the confidence approach would react to this because that sort of outlaying model would actually have an influence on where the boundaries of the intervals lie. And that sort of dissenting voice, metaphorically speaking, would be taken into account. And I think that's how it should be. So at this point, it's just an invitation to scientists to come up with the largest possible collection of physically plausible models that cannot be ruled out based on the data that are available. And that's what should be used as a basis for decision making. Now, the Giere thing, fast and frugal decision making, his examples are always sort of simple things like who's going to win the tennis game and stuff like that. So, I mean, we have a long history of people making gut decisions about natural catastrophes, and that's not a very successful one. That's why we're having this discussion. If there were people in government agencies or in med offices who have gut feelings about things, and there are plenty of them, don't believe me, and if they made the right calls, we wouldn't be here debating this. We are only here because people do write losses, they do miss storms. Kenneth was an example. I mean, they only started evacuating people less than 24 hours before the cyclone made landfall, which was too little. So that's why so many people died. So, I mean, just manifestly, gut feeling is not a good guide to action in these cases where you have large, complex, non-linear systems and a lot of lives at stake. So, I mean, if Gerd can convince me that there is a better, fast and frugal procedure, then, I mean, great. I mean, we're having no computational fetishism here. So if you can have it easier, that's great. But so far, no one has had the right guts.
Okay, so I'm going to take 3 more questions. And so 1, 2, 3, and then we'll be done.
This is just a quick question. At the beginning, there was an assumption that the models were independent and equally likely. Is that a dangerous assumption, or?
I wouldn't call this an assumption. It's something that has been relayed to us in conversation with the modelers. So we did meet with the modelers and we told them, listen, tell us. And we were hoping they would tell us something different. We were actually hoping they would tell us they have a best model and that you could center the intervals on the best model and then sort of move out from the best. But they were absolutely adamant that there was no way to discriminate between these 51 models. And at some point we just said, look, I mean, if those who work with these models say this, that's the best we can do. In the general description of the scheme, I said, you just assess the uncertainty by taking all scientific evidence that you can get your hands on into account. The best we could do is talk to the physicists and the scientists who construct and run these models, and if they tell us that they're all equally good and they can't discriminate between them. So, but that's different for other model ensembles. I mean, we had a project with an insurance company at some point that used North Atlantic hurricane models, and there was clearly one model that was best. They thought, this is the best model, so that's the one we trust most. And all the others are basically used to sample the uncertainty around the best model. And there we constructed the interval by saying the center is the best model, and then there were 13 models in that ensemble. So they've moved 5 out, that's the narrow interval, moved 10 out, that's the medium interval, and all of them are the large interval. So, but I mean, in brief, that's not a philosophical view, that's a scientific view.
So I had basically the same worry. I was going to ask if your framework can accommodate different confidences and the different models. And so you answered the question, but I guess I was thinking, is it really plausible given what Sam said about how different models use different types of data or distinct types, just this variation in there, it made me wonder if you can really rank the models if in some straightforward way and then be confident that they're equivalent as well.
We can rank them. I wouldn't call it straightforward. So, so there are. This is sort of a black art, which is skill scoring models. And that's in itself, that's why I said the black arts are complicated. There are, I don't know how many different skill scores, and they produce different rankings. But if you somehow settle on a particular ranking and a particular way of assessing skill that's relevant for the problem at hand, and you take that seriously, sometimes it's possible to say that model is better than that model. In the case that we're in, the physicists insist they can't, but in the other case, that with the North Atlantic hurricane models, you could. One of the 13 was the best, we were told, and that judgment was reached by applying a skill score. But then obviously you push the problem one back. So that judgment is not stable under a choice of a different skill score, or may not be stable under the choice of a different skill score. And I mean, that just shows how underdetermined these things are, and that's how the scientific uncertainty manifests itself in these contexts.
Hello.
Hi.
My question concerns your upcoming pilot with Madagascar.
Yeah.
Do you plan to try to validate your confidence approach in the pilot using multiple cyclones? And if so, what are your validation measures?
Yeah, multiple cyclones is not how I would put it, because we don't know how many cyclones we're going to have. So what we do is we have the system running in real time. So you get a forecast every 6 hours. The European Centre forecast that I mentioned, they're actually cover the entire globe. So they cover Madagascar. So these forecasts are available there. So we will feed them into the algorithm every 6 hours. So the calculations we've shown will be produced every 6 hours. And so alerts or no alerts will be issued for 10 different lead times every 6 hours. And the validation is, in a sense, well, how well does it track what actually happens? I mean, it's a pilot because we're not requiring the authorities to actually act on our alerts. So they have them at hand. They can do with them whatever they want. But we will definitely monitor. So if we get alerts all the time and nothing happens, we're definitely in trouble. Or if we have no alert and something bad happens, we're also in trouble. So the validation, I mean, we haven't settled on any particular numerical measure for validation, but we definitely compare the alerts with the actual actions. And if the alerts track what's really happened, as it did in Kenneth, then the system is onto something. And if it's completely uncorrelated, then we're having a problem and we have to go back to the drawing board and think again.
The question is whether not necessarily your technique, decisions that the government is making are right to.
Good. Yeah, no, that is a very good point, and that's sort of often coming up in that discussion. So that's why I'm emphasizing that we are concerned with providing alerts for anticipatory action. Look, if the relevant authorities don't act on them, there's nothing we can do. But we will work out a protocol with the authorities. So here is what you should do if you get a green alert 5 days in advance. Also, I didn't have time to talk about that. The idea is very much that you have staggered actions. So if you get an alert a week in advance, you can do simple things like putting sandbags out. That's a good idea. But you wouldn't evacuate the entire population. You would do that only 2 days in advance. So you would have staggered actions. And part of the approach would be that one has a worked out protocol about what happens when given a certain alert is issued. Now, if that is not followed, obviously we can't do anything. So that's beyond our control. That's for the authorities. But it's still interesting to see whether the alerts, that's why I'm careful to say we check whether the alerts issue track what actually happens. So there's a lot of information in that. And if the alerts really track what happens, hopefully the year after there is a good reason to say, well, this is more than a pilot where we just let it run on the side and see how it works, but we actually do something about it. And so that's the medium-term ambition.
So we've come to the end of our formal time, but we will be continuing the conversation right out in the hallway with refreshments at our reception. So please join me in thanking Professor Roman Frigg.